These are your 4-5A notes. We're going to now proceed in our last two ways of solving quadratics. So 4-5A involves factoring and creating perfect square trinomials. This is going to lead us into the next method of completing the square. So we're going to kind of take it in a 2-day fashion. There's a lot of information with this one. This one's probably the least favorite besides graphing. It is nice, but there are some issues with it as well. So before we move on about solving, we have to talk about perfect squares. These three problems are perfect squares of binomial factors. So when you look at that, a common mistake is that people just square the first term and square the last term, and what they get is an x squared plus 64. But you're missing your outer and inner terms. So what I always encourage kids to do is when you see the squared, sort of ignore the squared and write the quantity a second time, because that's what squared means. Multiply x plus 8 times itself. And so now you would see that you get 4 terms rather than just the first and the last. So when I FOIL this, I get x squared plus 8x plus 8x plus 64. And these middle two terms are exactly the same signs, exactly the same values, and that gives me the 16x. And so this becomes a perfect square trinomial. In the second example, instead of saying x plus 5 squared, I would say x plus 5 times x plus 5. And I would multiply the first terms, x squared. Outer terms gives me 5x. Inner terms gives me 5x. And the last terms gives me a positive 25. Again, the two middle terms are both positive 5x, same sign, same exact value. And so they become 10x plus 25. And the last quantity, x minus 3 squared, would become x minus 3 times x minus 3, which is x squared minus 3x minus 3x, and then a positive 9. Same exact signs. This time they're negative, which, because the original problem was negative, you can see where that's coming from. And you get x squared minus 6x plus 9. So what I like to do is, rather than have to show all that work, there's a little pattern. If we can understand the pattern, when we have to factor these things, we understand the pattern as well. So the pattern here that's formed is that when you square these things, you're always going to end up with, if you look up above, we had the first term squared. Okay, so to get this number, x squared is just that number squared. To get the last number, the positive 64, it's always that number inside squared, and they're always positive. So that holds true for all three of these: a positive x squared, a positive 25, positive x squared, positive 9. Even though it was a negative 3, when you square a negative 3, it becomes positive. And then if you look at the relationship of this middle term in here, this positive 16x, is actually twice that value. So if you took those two numbers inside there, the 8 and the x, and then the 8 and the x again, gives you a positive 16x. If you look at a 5 and an x, and a 5 and an x makes 10x. And then a negative 3x and a negative 3x makes negative 6x. So the idea of the pattern is that you can come up with that middle term without having to show all that work. You can actually come up right with the answer. So looking at these two equations, I can square the first term. That gives me y squared. I can square the last term to give me a positive 49. And then I know that if I were foiling this, I'd have a negative 7 times an x twice. So y. Negative 7y gives me a negative 14y. And so without having to FOIL, without having to show first, outer, inner, last, and then combine like terms, we can have the answer quickly. The only problem with this is that sometimes we forget that middle term. So you can always expand it out, but I just wanted to show you how that happens. In this example, square the first term, 4x squared, square the last term, positive 9, and then the middle two terms will be multiplied twice, your outer and your inner. So a 2x times 3 is a 6x. Twice would give me 12x. So those are perfect square trinomials. Now, I'm not really concerned with that, but I do think it's important to talk about how these things were formed in case we need to factor them. So working backwards, going through those, if I have a perfect square trinomial, I want to know that it's a perfect square trinomial and that it'll factor to something squared. So one of the tests is if AC is the same thing as taking half of the B term squared. That's a quick little check to see if these things are perfect square trinomials. And if they are, they'll factor to either A plus B squared or A minus B squared. So when I do these, I look at number one, and it just sort of looks like there's a 6 in there. I see a 12 and a 36. It looks a little different, and I have trained eyes for that. But if I take, this is my A value, right? This is my B, and this is my C value. If I say the A and C value, A times C is 36. And then if I take half of the B value, which is -6, and then square it, I get 36. Because they both match, that tells me it's a perfect square trinomial. Now, I wouldn't have to do that on paper. I could do that little test in my head. But knowing that tells me that this is going to factor to something squared. And you just sort of work backwards through what the other rule. To get x squared, we squared the first term. So the first term must be x. To get the 36, we must have squared the last term, and so that is 6. And then to get the negative part of 12, it was negative. And so we're working backwards to say, what did we multiply to get that? Okay? So it's a different type of way to solve this trinomial. You could do it the long way. You can make your sums and differences chart. Another way I kind of look at it, I can say what multiplies to give me 36 and adds to give me -12. If you get the same number, same exact signs, you know it's perfect. So even though you didn't recognize maybe this whole relationship, you could recognize it here, that when you get the same number, same sign twice, that tells me it's going to be something squared. Number 2, okay, I see a 144 and I see a 24. I'm hoping that same thing at home, you guys are seeing a 12 in there. There's got to be a 12 in there. So I go through my test. This is a 1. So 1 times 144. My AC value is 144. And then my B divided by 2 squared value. Let's look at that. My B value is 24. If I take half of it, I get 12, and I square it, I get 144. They match, so that tells me it's a perfect square trinomial. And so what that tells me is that this isn't going to be two different quantities multiplied together. It was the same quantity multiplied by itself. And then to get back to factor that, it's a little bit easier. What would I multiply together to get B squared? A B. What would I multiply by itself to get 144? A 12 and a 12. And they're both positive because the middle term is positive. So we could factor that the long way as well. But I like to introduce this B divided by 2 squared. It's going to show up in tomorrow's notes. So let's look at number 3. Number 3 could be a horrible one because of that 9. And so if I was going to go through this whole process and look for the different numbers, and I didn't see something, and I look at my A times C, and I get 900. And then my B divided by 2 squared, I'm going to check that number as well. The B value is -60. If I divide that by 2, I get -30. And its squared is 900. These two numbers match, telling me this is a perfect square trinomial. So that tells me that it's going to be something squared. Take, what would you multiply by itself to get 9x squared? A 3x and a 3x. What would you multiply by itself to get 100? 10. And then the sign has to be negative because of the -60. So now you can kind of see where the 60 is coming from, that 3x and 10 were your outer and inner terms. So the whole idea of this is eventually we're going to use this as a strategy to solve. So right now, today though, I just want you to recognize and make them perfect. So we're going to use the square root property to solve perfect square trinomials. So when they ask you to use the square root property, they're telling you you're going to have something perfect squared. So if you look at this trinomial the way it is, it's perfect. Okay, it follows that rule. the 1 and the 16 multiplied together equals 16. If I take half of -8, I get -4, and if I square it, I get 16. So that tells me it's a perfect square. So all of these in your homework are going to be perfect square trinomials if they ask you to use the square root property. So to use the square root property, we got to bring in something squared. So the very first step is just to make it squared. Okay, and this is the first time when we solve that we don't bring that number over. This is actually the only time that when we solve, we don't set it equal to 0. So I factored what was over here on the left-hand side, and then I wrote it equal to 25. Now I have something squared equal to 25. To undo a square, I'm going to take the square root of both sides. Okay, and the square and the square root cancel each other out. They're inverse operations of each other. So I end up with x minus 4 equal to, and the square root of 25, anytime you solve using the square root property, you have to say both answers. So positive and -5 work there. So what that plus or minus 5 is going to do is it's going to create two solutions. So when I solve for x, I have a little bit more to do. I need to add 4 to both sides. And when I add 4 to both sides, I'm actually adding 4 to a positive 5, which is 9. And I'm adding 4 to a -5, which is -1. So my two solutions are -1 and 9. If I were to graph this parabola, this quadratic, it would cross the x-axis at -1 and 9. If I plug those numbers into the equation, they will equal 25. So if I plug in 9, 9 squared is 81. 81 minus 72 is 9. And 9 plus 16 is 25. When I plug in -1, I get -1 squared is 1. Plus 8 is 9. 9 plus 16 is 25. So you can check your answer with the original again. So just a different approach. We are using factoring, but how we factor is we know that these are perfect squares. So we factor, we take the square root, and we solve. So looking at the second problem, okay, if they're asking me to use the square root property to solve, I should have something squared to take the square root of. So I look at these numbers and it's screaming a 3, right? So I need to get this something squared. So x squared becomes x, the 9 becomes a 3, and my sign is positive because the middle term is positive. So that trinomial factors to this perfect square, and it's equal to 5. Now that I have a perfect square, I'm going to take the square root of both sides. The square and the square root cancel. X plus 3 is equal to plus or minus the square root of 5. Now that's an ugly number. It's a decimal. It's 2 point something forever. We don't want that. We're just going to leave it as the square root of 5. So actually, it makes our job a little bit easier. I'm going to subtract 3 from both sides. And so x is equal to two solutions. It's -3 plus or minus the square root of 5. Now, there's actually two solutions there. You can write them combined, but it's -3 plus this ugly decimal and -3 minus this ugly decimal. These are on the graph, this is where it would cross the x-axis twice, but in really ugly spots. So we could just approximate the answer because we don't know really, we can't pinpoint exactly where it's at. So these are the exact solutions. Again, you can write them separate or you can write them together, but it has two ugly, irrational solutions. And the reason it's irrational, it has a perfect square, an imperfect square root of 5 there. The second half of your homework today is going to involve making a binomial into a perfect square trinomial. So it kind of leads into the next concept for tomorrow's notes. We're going to make everybody perfect. This process of completing the square is a process in making non-perfect square trinomials into a perfect square trinomial. So when you complete the square, you add on a value that makes it perfect. So a perfect C value is that b divided by 2 squared. Now this only works if your a value is 1. So it's a little bit more difficult when that a value isn't 1, but we're just going to work with when a is 1, okay? So that makes this true every single time. And in the very beginning of this lesson, we saw this value. That was one of our values to determine if it was a perfect square trinomial. So looking at these two examples, my b value in the first example is negative 6. Okay, right now what they're saying is x squared minus 6x plus c. They're questioning what would we put here to make that a perfect square trinomial. So I take negative 6, I divide it by 2, and I get negative 3. I square the negative 3 and I get 9. So the perfect c value that would go with these other two terms is 9. So that would create the perfect square trinomial, x squared minus 6x plus 9. In the second example here, my b value, this is my a value is 1, my b value is 8. We're looking for the c value. The perfect c value would be taking 8, dividing it by 2 and getting 4, squaring it and getting 16. So the perfect c value here would be 16. It always has to be positive because you're squaring it. So x squared plus 8x plus 16 is your trinomial, and it would factor to x plus 4 squared. And the one up above, x squared minus 6x plus 9, would factor to x minus 3 squared. Okay? So that's all we're going to concentrate on, using the square root property for ones that are already perfect, and then forcing them to be perfect if they're not. That's called completing the square. So if we look at these three examples here, okay, I'm going to take half of the b value, negative 10. I'm going to divide it by 2. I get negative 5. Put parentheses around it and square it. It equals 25. So 25 is the c value. Number 2, that's the work I need to see. I need to see what you're doing, the process. Take the b value, 14. Oh, this should be an m. Sorry about that. 14 divided by 2 is 7. 7 squared is 49. So the c value should be 49. And number 3, take half of the b value. Leave it as negative 9/2. It's a lot easier with fractions. Square the fraction, which means you're going to square the top, 81, and square the bottom. So 81/4. Get away from the decimals. I'm telling you, when we do more with these, it's going to be a lot easier if you leave it as an actual fraction. So that's really the only work I need to see, is you calculating the new c value. All right, so give the value of c that would make this a perfect square trinomial. That's just what we did on those practice problems. And then I want you to solve using the square root property. So what I'm telling you here is that this is already perfect. So your first step is to make it equal to something squared so that you can take the square root of it. Good luck.